A box with a square base and an open top must have a volume of a lot, a large volume. We wish to finish. We wish to find the dimensions of the box that minimize the amount of material used. All right, first find a formula for the surface area of the box in terms of only x, the length of one side of the square base. And we've got a hint to use the volume formula to express the height of the box in terms of x. So that's interesting. Let's see what that all means. So first, sketch here. All right, so I have a box, and it's going to need to be an open top box. Let me try again. Terrible with three-dimensional drawings. All right, so open top box. That's not bad there. Okay. So the base along each side is the same. It's going to be x. We don't know what the height of this box is. If we did, we could determine things like the volume is the area of the base times the height, or length times width times height, however you want to think about this. In this case, it would be x squared h, and the surface area would be the amount of surface area on the base, which is x squared, plus 4 times the amount of surface area on each of the sides, which is the same each time. It's just x times h. Now, this hint here, where is this? So use the volume formula to express the height of the box in terms of x. So we know the volume. The volume is, all right, 442,368 cubic centimeters. And we know that that volume is equal to the dimension x squared times the height. So effectively, we can figure out the height in terms of x squared if we just divide both sides by x squared. So that gives me h equals this value over x squared. Okay, now I'm working toward a formula for surface area. Okay, that was requested here. And I'm getting close with this particular equation, but I have more than one variable in it. So to make this work out, I'm going to take that surface area equation, and I'm going to call it a of x because that's what they're using in the nomenclature of the problem. Call it x squared plus 4x times 442,368 over x squared, which this x cancels out one of those x's and gives me x squared plus 4 times all this mess. So let me see if it's even worthwhile multiplying. So 4 times 442, 368. Oh, let's see, 1769. 472 all over x. And that right there is my area formula. So the next part of the problem says to find the derivative of this. So the derivative of this function shouldn't be too bad to find. I'm going to think of this in terms of this giant number times x to the negative 1 power, so that I can use the power rule to get this. So 2x minus 1769472 x to the negative second power. Simplifying would make that 2x minus this guy over x squared. Okay, and that's the answer to this next portion. Now, calculate when the derivative is equal to 0. So if I set this derivative equal to 0 and try to solve, and let's see, I could multiply both sides by x squared. 0 times x squared is still 0. This would be 2x cubed. These squareds would cancel, so minus 1769476. And I'm certain that I'm going to miscopy that number at one step and regret it. And honestly, looking back here, I think I have already done that. So let me fix this. 472 it was. All right. Yeah. Okay. Now I'm going to move this over, and I have the feeling that this number is so large and cumbersome that it's going to, at this step, result in something that is a perfect cube. At least we might have that working for us. 884736. And let's see, if I take the cube root of that number, all right, so math, cube root, answer, excellent. So x equals 96. And let's hope that it will just need us to work with 96 from now on, not something huge. All right, so that is the answer to the next part. So that's 96. We next have to make sure this value gives a minimum for the surface area, and we'll use the second derivative test to determine that. So, oops, that's weird. So what we will do is find the second derivative. So let's see, taking this right here, second derivative, so that would be the derivative of 2x is just 2, and if I bring, oh no, I do have to work with this number again. All right, 1769472. Now I have to multiply it by 2, so it's going to be plus 353 8944, x to the negative third. And what I need to do is check if I plug in 96, if I get a positive or a negative answer. So let's see. So 2 plus, oops, that answer times 96, well actually I could just say divided by 96 to the third power. We get 6. That's kind of nice. All right, now if we get 6 for the second derivative, that means the second derivative is positive. We're on an interval that is concave up. So if we are concave up, our curve would look like this, and any critical value we would come about would be a minimum. So this results in 6. Oh, no. So this is where we would put the second derivative, which we calculated here. And then evaluating it would give us 6, which would then verify that it's a minimum. And so this minimizes the amount of material used.